while we wait, maybe I can introduce the first speaker. This is Nick Antipa from Berkeley, and he's going to be presenting his work, which is video from stills, lensless imaging with rolling shutter. His joint work with Patrick Orr, Emra Boston, Ren Nig, and Laura Waller, all from Berkeley. And you can wait a minute before you start.
Okay. Before I start, can everybody hear me okay? We're trying the new hands-free microphone. Is it good? Louder? Okay.
Take it away.
Okay. Thanks for the intro, Ashok. I'm really excited to be here today. Today I'm going to talk about my work with Patrick Orr. He's an undergrad who I actually recruited for this project. We contributed equally to this. And I'm going to be talking about lensless imaging with rolling shutter and show that this enables compressive video. So a quick overview of direct sampling for video. So in a typical global shutter approach, there's a dynamic scene, which is depicted on the left here. And a single short exposure is captured using usually a lens and a standard sensor. This exposure is then sent to an analog to digital converter, which spits out an image. And then as the dynamic scene evolves, a sequence of still images is recorded. So this works great, but unfortunately, in order to go faster, you basically have to speed up the analog to digital, which can be done, but usually at great cost. So this is an example of a commercial high-speed video camera. This is a Phantom V2512. This thing can record a megapixel at 25,000 frames per second, which is very impressive. But to do it requires quite a lot of electronics. So the total system is $180,000 US. I don't know if you can see that behind me. And it weighs 8.1 kilograms, or 17 pounds, and that's without the lens, right? So that's basically what it takes to do this with direct sampling approach. The idea behind compressive video, which is what I'm going to talk about today, is to be more efficient and break this trade-off by encoding more information into the same bandwidth budget. So in compressive video, the dynamic scene is moving while some kind of a space-time encoding optical and sensor system is recording multiple frames. These frames are then encoded into a single exposure. That one exposure is then converted to digital, and then a computational reconstruction is performed from this one frame, expanding it back into the sequence of stills that comprise the video. So the point here is that this reduces the load on the ADC, so this thing can capture more information with a fixed bandwidth budget. Okay, so this is a field that has been around for a while. Most of the approaches to this rely on temporal coding. And this in theory, would require redesigning the chip architecture to be something other than global shutter. Because this is typically infeasible, a lot of approaches to do this have used complicated optical setups to simulate some kind of a hypothetical temporally coding sensor. So one approach to this by Patrick Orr and company is to use a coded aperture. So in this case, there's an amplitude mask that's placed at the focal plane, which then has to be translated with a piezo drive during exposure. The flutter shutter uses a ferroelectric shutter placed in front of the lens, and this does the temporal coding into a single exposure. SLMs have also been used in the focal plane, but that requires reflective geometry. And there's been some theoretical work at looking at randomly spaced or programmably spaced rolling shutter sensors. And this idea had a lot of promise, but a real sensor, to my knowledge, was never realized out of this work. So what we're going to do today is I'm going to show you that it's actually possible to take a simple lensless camera and combine it with a rolling shutter sensor, and this will naturally enable compressive video. So I'm going to go through that, but at a high level, what goes on is that the camera consists just of a diffuser placed in front of a rolling shutter sensor. And then as the scene moves, the rolling shutter acquisition happens, and out comes a single rolling shutter capture. This capture is then fed into a sparsity-constrained inverse problem, and the result is that we can recover 140 frames of video at over 4,500 frames per second, all from a single exposure in this simple camera. So to understand how this works, first I'm going to go over how the rolling shutter process exposes an image. So the idea here is with rolling shutter, each row of the sensor is exposed over a unique time window. So on the left, I'm showing the row Y and time T, and on the right is what the sensor is seeing. So we see at the very, very beginning, just the top row is actively exposing, and all the other rows are not doing anything. And then as time evolves, we see that there's this exposure band that sweeps down the sensor. So if we pause this, we see that there's a band of pixels exposing in the middle, shown in blue. The red pixels are currently reading, and then the orange ones are done. And a key point here is that this is happening incredibly fast. So in most rolling shutter sensors, the faster it goes, the better, the closer it approximates global shutter. So there's been great work put into making this happen with under 10 microsecond delay from row to row. This corresponds to hundreds of kilohertz. So this is an incredibly fast phenomenon. And I also want to point out that for this work, we're actually not using a single shutter sensor. We're using a sensor that has a dual shutter. So it's the same idea, except in this case, there are 2 exposure bands that sweep outside in. In math, what that looks like is we can represent the actively exposing pixels with an indicator function, which we'll call S. And the idea here is this is just 1 for any pixel that's actively recording, and it's 0 outside of the exposure band. So what that means is that the measurement B, given some dynamic intensity at the sensor, which I have detailed out here, is just the integration over time of the shutter function times the dynamic intensity at the sensor. Okay, so that's the rolling shutter exposure model. So now let's move on to the optical models. So in this talk, I'm going to talk about one-to-one, like traditional lens-based imaging optics, as well as using a lensless diffuser-based camera. And first up, I'm going to talk about lenses, and I'm going to discuss why a one-to-one imaging system doesn't work well with rolling shutter for compressive video. Okay, so to do this, we're going to think of, it helps to visualize the scene as a 3D volume. So to illustrate this, I've got a really simple scene. So this scene just is 3 light sources that will flash at distinct locations and times. So the video would look something like this. So we have cyan, and then magenta, and then yellow, all at unique space-time points. So what that means is that in 3D, if we think of this as a volume, these occupy unique voxels in 3D. And because rolling shutter is column parallel, that is, there's no X dependence, for the rest of the talk, we're just going to look at 2 projections, XY, which is sort of the front-on view of the volume, and then YT. We're just going to ignore X. Okay, so now what I'm going to do is walk through how the rolling shutter acquisition acts on this volume. So on the left, I've got the dynamic scene here, and on the right, I'm going to show the measurement as we acquire the rolling shutter image. What you'll see, and then this is the equation just for reference. And what you'll see is that in 3D, the rolling shutter acquisition process is essentially a slice through, or 2 slices through in the dual shutter case. And so if we look at the measurement on the right, we can see that 2 of the point sources survive the acquisition process. That is that the shutter function overlapped with the magenta and the yellow, but we've completely missed the cyan. And this is interesting because this tells us that from this measurement, we know a great deal about where and when these 2 point sources happened, right? Because we know where the shutter function was. But we have no idea if any event happened at this point in the 3D space. And this is why one-to-one optics, like standard imaging condition lenses, won't work for compressive video here. You would essentially have to rely exclusively on priors to recover this point. So basically it's impossible to go from here to here. All right, so that's why one-to-one imaging optics like lenses are not going to work for this compressive video scheme. Now I'm going to introduce lens-based diffuser cameras and explain why this will work well for compressive video with a rolling shutter sensor. So first, I'm just going to do a quick review of imaging with diffusers. So basically the idea here is that the camera consists just of a diffuser and a sensor. So if we look at an on-axis point in the scene, if we carefully select the distance from the diffuser to the sensor, then this point will create a high-frequency, high-contrast caustic pattern on the sensor. And then if we look at what happens at a different point in the scene, we essentially just see a translation of the caustics. And then if we assume linearity, then all of the caustic patterns will add, and the final measurement will look like a linear combination of a bunch of these pseudo-random caustic patterns. So it's pretty unintelligible. This obviously is not a good representation of the scene, and so we're going to use inverse methods to get back the scene. The way we do that is conceptually, we think of the sensor measurement as a vector B, and we model this by multiplying the scene X by a matrix whose columns consist of the various point spread functions for all the possible points in the scene. So this is conceptually the linear forward model, and we can put this into an iterative reconstruction problem solving a standard non-negative least squares. And just as a note, in practice, we don't actually use an explicit matrix. We assume shift invariance and use a cropped convolution model here to make it fast. And we also add a total variation prior, mostly for denoising purposes in this case. So the raw data out of a camera like this looks something like this. So It's pretty unintelligible, kind of unsurprisingly. This is what diffusers are for, not for imaging. But after solving this problem, it's possible to recover a 2D image that looks something like this. So this is my coworker, Grace, who I did the early work on this with. So you could ask a question at this point, which is, what if we were trying to recover a single frame from the rolling shutter video? Could we do that? And so to take a look at that question, we could take this same data and we can ask, what happens if we try to recover that image from just these two bands? So this would be a single instant during the rolling shutter acquisition. And what we see is that with just this simple spatial model, it's actually not possible to get back a high quality image. So this is obviously very, very badly degraded with a pure spatial model. And so in order to fix this, what we need to do is we need to go to a full 3D space-time model. So I'm gonna go over the space-time model, which is basically combining the diffuser camera with the rolling shutter model. Back to our simple object. Just to remind you, it's 3 point sources at unique space-time points in the volume. So I'm showing the YT projection up here, and I'm just gonna walk through how the final intensity of the sensor would evolve in the diffuser camera. So we have our first point, cyan, and the XY projection looks like this, so it's just a single point. This then gets spatially convolved with the caustic pattern, and what comes out is simply the result of this convolution, which is a heavily multiplexed 2D measurement. And if we look at that again in this YT space, we see that the information has been spread vertically, so it's been spread out in space, but it hasn't been spread in time, right? It still flashed when it flashed. So that's why we get this vertical streaking. So we can store that down here and move on to the next point. So we look at magenta, and the same process occurs. The key difference being that while it's still spread in space, it happens at now the distinct time point. And we repeat this for yellow. And the final result is that the volume, the video, if you will, at the sensor looks something like this. So similar to the previous diffuser cam images, it's a little bit of a mess. But we can take a look at how the rolling shutter samples this to understand why this is actually a good thing. So if we take a look at the YT slices of the multiplex dynamic scene on the left, again, on the right, I'm gonna show the measurement. And what we see is now, as we slice through this volume with the rolling shutter function, we're catching information about all of the points that were in the scene. And this is the key to making this work, is that because we're spatially multiplexing, the rolling shutter can basically see every point in the scene. Okay, so in math, the complete space-time model is we take the frame estimate at time 1 and spatially convolve it with the caustics, pointwise multiply by the shutter function for time 1, and then so on. And then the result is summed over time. A key point here is that the caustics are not changing with time. It's just the frame and the shutter function that vary. So this is a pure spatial convolution. So in math, what this looks like is that the sensor measurement B is just the sum over time of the shutter function times the PSF convolved with the video over space, which we'll denote as a matrix A. Okay, so what that looks like if we think about the matrix vector space, is that this is an extremely underdetermined problem. So what we're trying to do is we're trying to solve for, in our case, 140 video frames from a single measurement. It's a very underdetermined linear system, and this is where the compressed sensing comes in. So if we try to just use a standard non-negative least squares, this wouldn't work. But the key to making this work is we add this space-time prior. So in our case, we just use a sparse gradient prior. So this is saying that the gradient should be sparse in space and time. And this is the key to making it work. And then recovery can be done just by using any iterative method. And in our case, we use Vista. Okay, so experimental results. So back to the scene I showed at the beginning. Remember, the object is this little, looks like the pinwheel from a Mac. And the raw data looks something like this. It's fairly unintelligible, which I think is unsurprising. But we can ask ourselves what happens if we do a simple 2D deconvolution. So this is running the standard space-only model. And what we see is, unsurprisingly, a lot of motion blur and artifacts. But then we can take the same raw data over here, and we can run the space-time model on it, and we can recover 140 frames at 4,500 frames per second, all from this single measurement. Okay, so here's just another example. So in this case, what I'm showing is this is a single frame from a static scene. Again, we can run the 2D deconvolution. And now what I'm gonna show is sequential 2D deconvolutions for multiple frames captured out of this scene. In this case, Patrick is gonna bounce the tennis ball on the book. What we see is that this is happening very fast, right? If you look with your eye, this is maybe a single frame the bounce happens. So if we pause it here, we can see that if we do a reconstruction during the bounce, there's quite a bit of motion blur. But just like before, instead of motion blur, we can take the same measurement and run the space-time deconvolution on it, and we can get back the actual bouncing event as it occurred during this single rolling shutter capture. And a final example, we wanted to recreate an iconic high-speed imaging scene, but we're not allowed to have bullets in Laura's lab. So instead we used foam bullets. So this is an apple, and I'm shooting it with a Nerf gun. That's all I was allowed to have. Yeah, and so again, this is a 540 by 640 pixels at over 4,500 frames per second. Okay, so I have a minute left, and I'm just gonna go through potential and limitations. So potential, right now we're getting about 4,000 frames per second, but in theory, this could be going at the rate of any rolling shutter system, which can be under 10 microseconds or over hundreds of thousands of frames per second. In order to get there, we need high quality designed diffusers. We currently don't know what the optimal diffuser would be. We're using random for now. This is an open question. And better video priors would, of course, improve the quality. Limitations, we're relying on video sparsity, so this only works if the video is actually compressible. We're using dual shutter now. We're actively working on getting single shutter to work, but for now we do rely on dual shutter, which it is off the shelf, but it's less common. There's a lot of noise. We need quite a bit of light to make this work because it's a very short exposure time. And it takes about an hour to 2 hours to get back a video. So it's a very large convex program we have to solve. And lastly, there's a delay in the read time between frame to frame, so we can't actually stitch together multiple reconstructions without a gap. And with that, I'll thank my co-authors and take any questions.
Are there any questions for Nick?
Very nice work. So it seems like when I look at some of the final set of results where you show 2D with motion blur, and then the 3D one where you can actually resolve much higher time resolution, you see the classic loss of spatial resolution to get higher temporal resolution, right? And this is sort of what binning would provide you. Lose spatial resolution, but you can get higher temporal resolution. So I'm curious if you sort of computed like space-time bandwidth products and seen how much actual improvement do you get over the, sort of the ADC rate?
Yeah, okay, so if I understand the question is, how would we do if we just bend the sensor to run it faster? Because that reduces what has to
That's one way of posing it.
Yeah.
The other way is like, what are the benefits over that?
I see. Yeah, that's a great question. So we actually compared in the paper. We looked at a simple test object that was just a few LEDs flashing. And this is perhaps a little bit unfair because in that case, it's extremely sparse in space. So sort of the complication with compressed sensing systems is that in practice, it's very hard to actually say what the reconstruction quality will look like. I don't know the RIP constants for this system. So in that case, though, of a simple object, we can do far better in terms of space bandwidth product. So it's effectively running at, I believe it was 5 to 10 times the effective bandwidth. But it's a very simple scene, but in much more complex scenes, then we basically have to over-regularize to resolve anything in time, and the loss in spatial resolution would be worse than if you were to just bend. So basically it's object dependent is the answer. Did that answer your question? Okay, thank you.
Thank you for nice work. And in the introduction, you actually complain about the regular, random-like, sampling system is so complicated, right? But the rolling shutter still have a x-axis consistency. So but if you, using more, the program like, the pixel-dependent, the program sensor, the quality is getting, higher, or it's still similar?
Yeah, so is the question, how do we compare to, if you could build a sensor that actually had programmable exposure?
Yep.
Yeah, that's a great question. We actually don't know the answer to this. We're looking at collaborating with, I don't know if you've heard of they have a 2-bucket sensor. So we're actually looking into that as a design problem. Again, it's because it's a highly nonlinear reconstruction, it's very hard to actually say. But I think that's a great question, and we're looking into it.
Any other questions?
Could you elaborate a bit on what you said at the last slide about how there's a delay between frames? I guess that's only if you have extremely short exposure times, but a rolling shutter just rolls continuously, so I didn't understand that.
So it's actually I highlighted something a little bit there. There's sort of two issues. One is just purely implementation-wise. The sensor that we're using really short exposures. So we're using 500 microsecond exposures. And so there's a fairly long delay in terms of the actual read time of the whole frame before we start to get the next frame. There's also a second issue, which is related to the aperture, which I can talk about with you offline. But we get some artifacts at the beginning of the video that are a consequence of our particular geometry. And this also destroys information at the beginning of the frame.
And I have one question. This is in relation to some of the work that was presented earlier today about measuring wavelet coefficients directly. And you could imagine that those kinds of adaptive techniques could also be used to achieve the same end effect. Do you have any sense of how these things would compare, or what the trade-off space would look like?
Yeah, my thinking on that, I mean, I'm thinking out loud here, but I think something adaptive would probably work if you had something periodic. So if you could sort of take an image and then figure out where you need to focus on the next round and so on. So if it was periodic, you could probably do very well with that. The idea here is this is not adaptive, so this should generalize better to just a single shot. That's how I would think about it, but I don't really know.
Thank you, Nick.
Okay.
Let's thank the speaker again.
Thank you.